thanks for joining us, everybody. We have folks all over the world. I heard that there's somebody from Italy here. So the last Friday of every month is kind of dedicated to a general overview of something that would be useful to students, a different skill or something like that. So could I get a digital show of hands if you are a student? Okay, cool. Now, how about if you kind of know what predictive modeling is, you kind of know what GIS is, but you don't really use it that much. There's not that much utility in your everyday work life. All right, awesome. Cool. So today I'm going to be talking about archaeological predictive modeling. So we're just going to be going over what it actually is. Oh, it looks like we have a little, there we go. What predictive modeling is, what archaeological predictive modeling is, common problems, and proposed solutions with some of this. How we integrate archaeological predictive modeling with climate change, how you can get started, and where you can learn more. So predictive modeling in archaeology is actually a set of techniques. It's not a theory. It's a set of techniques where we use the location of known archaeological sites or cultural resource materials, and we base that sample on a region of fundamental notions concerning human behavior. So what that fundamentally means is we have a ton of locational data of archaeological sites, the location of archaeological sites paired with different attributes. So in what environment do we know that archaeological sites exist? And then we try to use that information to understand the overall effects that are most likely to produce a location of an archaeological site. Now, I know that when I'm talking about this, it sounds very distant from human culture, and we're going to get into that in a little bit. But overall, we're going to talk about some of the tension between statistics and some of these statistical techniques and the anthropological and archaeological questions that we're asking, because there is a lot of tension between the two. So some of the basic steps of every model ever are identifying the problem, articulating what questions you hope to answer with the model, and then gather different data, different kind of sources and different kind of types of data. So you don't really go into this blindly, and it's really important to have a set of questions beforehand so you don't really build this erroneous model. So overall, these are the more complicated steps that every model should be taking. We have initial data preparation and data cleaning, which frankly, that takes about 50% of my time when I'm actually preparing to build the model. You create and calibrate the model after deciding what statistical techniques you'd like to apply and integrate together to understand these broader patterns of human culture. And then you finalize this model and you evaluate it using different statistical testing techniques. Typically, archaeologists will select a sample. So we'll use probably 70% of the known archaeological sites to train the model, and then the other 30% of those locational data to test the model. So you're not creating this sort of self-contained model. You have to be able to go back and recalibrate your model. So this is an iterative process. It's not something that can be done quickly or automatically. You always have to retest and reevaluate what affects or what is affecting the model. So if you were to change one little bitty attribute, does that change the whole model or does it stay consistent? So I'd like to go over a few terms that I'm going to be using fairly frequently. Overall, there's the word binary, which is sort of the language of computers. You use zeros and ones. In our case, to sort of train a lot of these predictive models or site locational models, you're using, assuming that the landscape is a grid, and anywhere there is a site, you have a 1 for site or a 0 for no site. There are statistical issues with this, or there are issues in archaeological modeling with this, but we'll talk about that in a little bit. I'm going to be using geographic information systems or GIS. This can be run through programs called Esri, R, or QGIS. There are a lot of others, but GIS is a geographic information system. It's also a kind of program, so it's kind of a misnomer oftentimes. Predictive modeling is a kind of data science. So even though I'm an archaeologist, I'm an anthropologist, it's really doing data science and visual analytics. So the techniques that we use here could easily be applied to economics, to biology, to ecology, all sorts of different things. So the statistics are going to be really similar depending on your field, but the questions you ask are going to vary quite drastically. And some of the bigger picture questions that you ask are really going to vary. So we also have a site suitability model. That's the sort of correct term for a predictive model or an archaeological predictive model. And I'd like to sort of affirm that the term model means a lot of different things. So when you see the word model, when you read the word model in a paper, it can mean a lot. So don't think that this is sort of a one-size-fits-all thing. So I'm talking about site suitability models here, which is where we know the location of some archaeological sites. We have environmental attribute data. We might have some cultural attribute data, such as where people walked or what people were trading with and where. So those sort of combine to allow us to estimate the location and type of sites that we have not yet identified archaeologically. So for those of you who are not archaeologists, we use some of these terms interchangeably. An archaeological site, a cultural heritage site, or a cultural resource. These can be all kinds of things. So it can be anywhere from a piece of debitage, which is a piece of a rock that was shed off from a lithic material while it was being formed into a projectile point or knife or something like that. Or it could be a lighthouse. It could be the Etowah Mound. It could be basically anything that's over 50 years old, although that's a little reductionist. I'll also be talking about DEMs, which is a kind of data called a digital elevation model. From a DEM, we can get all kinds of different data types. And I'll show you a particular example of that soon. Next, I'm going to go over vector and raster data, continuous and categorical data. So we have vector data on the left, raster data on the right. A vector is a point, line, or a polygon, whereas a raster is a grid and there's a number behind the grid. Now, when we're using predictive modeling techniques, there's a really big difference between how we treat vector data and raster data. So the most important thing to know from this is that maps are really, really cool. They're beautiful if you do it well, I guess. But it's really the numbers behind the map that's the most important thing. So in this example, we have the geological profiles of Georgia, because Georgia archaeology is really cool and the state is incredibly varied. So you just see polygons of different kinds of attributes. On the right, we have a raster of a digital elevation model. So that's what it looks like when I say DEM. And every single pixel has a number behind it. So some of the applied effects of having a raster is that it's going to take a really long time to load, and you're going to have to use different techniques in GIS to actually analyze some of the raster. So a lot of times when you're building these models, you have to convert vector to raster data and go back and forth. So there are a lot of pretty easy ways to learn this, but it's something to be aware of, the difference between a vector and the difference between a raster. Now, similarly, there's also categorical data, which would be the image on the left, and continuous data, which would be the image on the right. Categorical data is where there's category. Continuous is where there's a continuum of numbers. So it's generally tied into vector and raster data as being categorical and continuous, but it's mostly the case. All right. So going from the basics to some of the theory and the data types that we can use. So here we have samples of some of the input data that I would use building a model for Georgia. So we want to know where in Georgia would we find archaeological sites given the known location of the over 60,000 sites that we do know. So I use a mix of raster and vector data, a mix of categorical and continuous data, and then I use that training sample of the point data. This would be what we call NARGIS, or Georgia's Natural Archaeological Historical Repository of GIS. So on the top, you have soil data, slope data, You have different rivers at different categories. Those are all sort of organized by degree. Geology aspect, which is the direction of the slope, and then DEM. Now I want to point this out. That looks gross, but it's really important because, as I mentioned before, most of my time is spent cleaning the data. So the digital elevation model for Georgia is so massive, my computer isn't capable of processing it all at the same time in GIS. There's a few sort of backdoor ways to do it, but this really good example, the data are fine, even though it looks super ugly there. But it's important because all of these data can be on different sort of scales of analysis. So there's a lot of mountains in North Georgia, so there's a ton of elevation. And you can see those really kind of beautiful dendritics of the rivers going out to the Georgia coast, and the scale of analysis of the digital elevation model changes. So a lot of time when you're creating predictive models, you need to rescale the data and resample the data while making sure that you still have integrity of the data. So you don't want it to be meaningless because you've made it go through so many permutations. So just another sort of thing to think about when you're looking at models, when you're reading all of these things and critiquing them, is what steps did the author or the analyst take to ensure that all of the data types are compatible with one another so that you don't have errors between them. So on the left, there's a really great book that if you have any interest in archaeological spatial analysis, I recommend you get. It came out in 2020 and it's about 25 chapters of all different kinds of archaeological spatial analysis. And what's great about this book is that they use, every single chapter has a really robust literature review. So if you're looking to get started in this, this book would be a really great place to start. But one of the keys is looking at inductive versus deductive archaeological predictive models. And this is sort of subsumed within this book. But overall, there are the two types. You have inductive and deductive. Inductive is data-driven. It's usually based on proximity analyses. So saying, how far am I to a river? How far am I to a source of clean water? Am I on a flat slope? Or how long is it before I find a really steep canyon? And a lot of the models that we talk about are going to be based on these proximity analyses. And those are drawn from the environmental data that I presented earlier. So looking at slope, distance to water aspect is important in some areas. And you're looking to the distance from a person or a settlement to a resource. We'll talk about some issues with this approach later, but it's a really, really good place to start. It's approachable, and it's sort of been a fundamental step for archaeologists to break into some of these bigger picture archaeological analyses and predictive models. So a lot of this is based on the fit of the points to the attributes. So you really smush all of these together. So you have the degree of slope, what would be useful for someone to live on. You have the distance to water. We assume that people want this clean water. We assume that people want soils that are fertile. We assume that people want soils that drain pretty well too. So we fit all of those attributes, we smush them together using a logistic regression, which I'll show in a couple slides. And this sort of output shows us the areas where all of these factors fit together on a spectrum. So we again have this sort of binary analysis. So there's no chance that a person would live here. A person would live here based on the fit of all of these points. On the other hand, we have a deductive analysis, which is becoming more and more popular as we have more computing power and as statistical approaches are really just blossoming into a lot of this artificial intelligence and especially machine learning. So we're using a lot more exploratory statistics like Monte Carlo simulations, ecological niche modeling, which is asking really similar questions that we are, except it doesn't assume the culture and the fact of choice. So it's saying, what's the most likely area where a black bear would live? And then you look at the environment and see what the most likely area would be. It doesn't take into account a lot of these bigger picture, more hypothetical questions that we're asking. And then also we can use Bayesian statistics, which is great because it allows for us to set up a series of priors, or we're allowing ourselves to use information that we already know, rather than kind of reinventing the wheel using this normalized sort of bell curve statistic that we would use kind of with a logistic regression, even though that's linear. Anyways, the deductive analysis more often involves human agency because we can have more of these experimental questions. So we're really pushing the boundaries of a lot of the archaeological knowns. So we're having more inferential statistics, and we're trying to interpret some of the patterns that we see. So here's what it looks like when we're looking at a regression statistic or a generalized linear model. A general is where you have parametric data, or normal data. Generalized is for non-parametric data or non-normal data, and humans usually produce non-normal data. So we have the generalized linear model, the general additive model, which is becoming more popular in recent years, and the weighted overlay analysis, which actually lets you weigh the effect of certain attributes. On the other hand, we're using other really experimental tools, which are rooted in machine learning to a certain degree. We have things like maxent or maximum entropy, which is really popular for ecological niche modeling. We can use random forests, which is based in regressions, but it still uses this sort of recursive system where you have an output, that output is re-input into the model, and then the model is run again. And then things like fuzzy math, which I'll talk about more, but it's my new favorite thing. All right, so here's a few case studies of predictive modeling. And before we get into this too much, I'd like to talk a little bit about really how much archaeological predictive modeling has moved forward. We have a lot of different factors going at once. We have new archaeological data, which is always improving. We're always excavating more sites and introducing that into the compilation of archaeological knowledge. So a lot of predictive modeling is using these syntheses. We have computational growth. That's one of the biggest factors. I'm sitting on a laptop right now with an i9. It's smaller than my notebook, and I can process data files for the entire country. It's amazing. So as we get more computational power, it really opens new doors for these analyses. And so now GIS even has a lot of artificial intelligence and machine learning just built in. What you would have to program using Python mostly, that's sort of the language of GIS. You can just click a few buttons, and you do have to clean your data. That takes a lot of time to do it properly. But when you're actually doing the analysis, a lot of times you can pre-program a lot of the steps just because our computers are getting so good. The memory is better, the graphics are better, and we know more. And then finally, we've moved forwards a lot statistically. Now, I'm not a statistician. I've taken a handful of classes and I read a lot about it, but we know a lot more, and we've been able to apply a lot of these statistical techniques to ecological and archaeological questions. Now, a lot of archaeological predictive modeling is really founded in ecology. So you'll see a lot of critiques about environmental determinism, which we'll talk about later. But we need to remember sort of the fundamentals of predictive modeling when we get into that. So, all right. One of the first models that came up is the Minnesota model. It was developed starting in 1996, and it was used to estimate the probable location of archaeological sites to help Minnesota Department of Transportation to avoid impacts to cultural resources. It was really developed as a way for the overall structure of DOT to save money. And they did a bunch of different independent results later and predicted that the sites were predicted 28 to 89% better than random chance. Now, yes, that's a huge margin. Minnesota is a huge state, and it's one of the first models, and it really broke a lot of ground. There's been a flood of states creating predictive models since the Minnesota model. So a lot of times you'll see it abbreviated as MNMO. No idea how you say that, but it looks cool. And it gives us a really good idea of where we're most likely to find archaeological sites. So if you're planning a road, you can look at this and preemptively reroute a little bit. So that's the concept of this. There's the Pennsylvania model, which is an inductive model. It's also used by the DOT before surveys, and it's extremely well documented and very transparent. I've linked the PDF in here if you want to see, but they've got 5 volumes about how they created this model. And that's the purpose. And what we need to keep in mind when we look at a lot of these models is how far we've come. So models aren't made to sit around. They're made to continue developing after once, which is exactly what's happened with this Illinois model. They've been working on this for decades, and it's beautiful. It's really, really well done. This is a Bayesian model, and which means that they've been using data that they already know about to create this series of what's literally called priors, or prior information, so that you can better refine and better define your questions. So for all of these, I have a link down at the bottom or in the notes if you want to look at these later on. So for this, they use a 30-meter DEM, so you can actually go online and zoom to any sort of area. There are also different protective steps that people use to maintain the integrity of archaeological site location data. So that's sort of another layer of things that if you'd like to talk about later, feel free to ask a question, but for now, we'll just sort of skip past it. So the big question now is, how do we add expert knowledge to the model? You hear people talking all the time. Any of us that have done CRM, we can look at a landscape and say there will be a site there will be a paleo site there, there's going to be a historic site there. And how do we quantify these independent in-field abstractions? So we have the belt buckle test about slope. Still don't know what it means, but every crew chief that I've talked about tells me to use it. But another way is there wouldn't be a site if you're not going to pitch a tent there. People like to live where we would like to live. If you have soggy feet, or if there's a bunch of moss or ferns on the ground, you're going to have a different kind of site. If there's magnolia, it's going to be a well-drained area. Cedar, there's going to be tabby or different historic resources. And then also people use hardwoods all the time. Well, we can't really identify the location of hardwoods from the Paleo-Indian era. So how do we digitize this and then create this layer that we can actually apply to archaeological questions? How can we use modern data, modern abstractions from the modern landscape to these past questions? And then also, how do we verify some of these case-by-case guidelines in an effective way that can be written into these statistical models? What's the level between an abstraction that's there for the sake of being there or something that is analytically useful? So archaeology, we have a lot of these loosey-goosey laws of, we know something's going to happen, but how do I put that into a raster file? How do I create that? And in statistics, a lot of times I kind of think of them as the uppity starch white shirt laws. You don't deviate from them. That is the law. There's not that much wiggle room. It's the constant. And then we are adapting our archaeological tests to these constants. So something to keep in mind. All right, so here's the biggie. I think archaeological predictive modeling is great. I think it's so useful, and there are tons and tons of different applications, not only in these really applied scenarios like DOTs trying to plan some of their roadways. If you're going to build, where can you build without being likely to run across a site that would halt your construction? How do we preserve these cultural resources? That said, it's important to define some of the problems that we have so that we can know what we're getting into and how we can find different solutions. So I have a series of problems and proposed solutions that I'd like to go over when we're thinking about building our hypothetical predictive model. First up, boundaries. Boundaries don't often exist in the real world. Yes, we have boundaries between river and not river, site, not site, but what does it really mean between some of these different regions? Is it precise? It's statistically necessary, but a lot of these are artificial. Something that's really cool now is the fuzzy inferential system. So the process is called fuzzification. All right, so the way that this actually works is we have sort of these abstractions. So I'm going to use short and tall. I see a person that's like 6'4", say, wow, you're really tall. I'm going to see a person that's 5 feet. I'm going to say, yeah, you're kind of short. But what about somebody that's 5'4"? Is that going to be short or tall? Hand up if you think it's short or not short. Okay, yeah, so it's kind of short. What about 5'5"? Short, not short. All right, so we've got some kind of wiggle room. And that's the purpose of the process of fuzzification, is we've got these boundaries between short, not short, tall, not tall. Well, what does that mean in the archaeological world? We have all of these sort of intermediate zones. So what fuzzification does is you can look at these different lines and see what proportion of that is between this binary system. So you have some people that are sort of short, sort of not short, some people that are sort of tall, sort of not tall. But as you reach a certain barrier, say 5'2", then you would be considered short by 90% of people. As a short person, sorry to other short people for picking on us. But this is how fuzzification works, is you have these built-in statistical abstractions. And this is what it looks like. This is a really cool example by Ed Gonzalez-Tennant, who has a fantastic series of QGIS tutorials that I have linked later on. He's predicting the post-apocalyptic geography of zombies using fuzzy logic. So the way that this works is you still have that sort of suite of data that you're going to be compressing into one different model. This could be the zombies are probably going to move slowly, so they're going to be close to a city. They're not going to be close to water because we all know zombies can't swim. It's going to be close to resources of people. So we can look at a lot of these sort of questions that go in to the fuzzy model, and then you sort of dissolve boundaries in a certain way. So the boundaries are actually probabilities of the impact or existence of that boundary. So that's a really good way to get away from the issue of boundaries in archaeological modeling for suitability models. Problem number 2 is environmental determinism. The majority of archaeological predictive models have been critiqued for being environmentally deterministic. Now, that's true. Yeah, they are oftentimes environmentally deterministic, but it's for a good reason. And this is where we talk about, again, the boundaries between archaeological questions, available data, and the statistical techniques that are at hand. So we have a lot of state site files and we have a lot of aggregate data, but how much of that aggregate data is available in vector or raster that we can pretty cost effectively implement into a research design? So a lot of the models right now are driven by environmental variables, but we're moving forwards from that. We're anthropologists. So what people are beginning to do now is model trade networks, look at good travel routes. Where did people travel? How did that change over time? How much time did it take for them to travel using the Tobler walking formula, which actually estimates how long it would take a person to walk carrying a backpack of a certain weight up a certain slope. You can integrate that into some of these models, which is down at the bottom. And then we can use CircuitScape, which I really want to experiment with. And that's using different energy theory. So if you have one quantity of energy at a starting point, given different routes, let's say through the Smokies, where would people be traveling through? Where are the passes in these mountains? Where are resources available? So although it's still based in environmental attributes, there are a lot of ways that we can integrate how people move. We're talking about resilience theory. Where are resources for people? What happens when these systems collapse? Historical ecology and landscape theory all integrate how people react to their surroundings. So we're beginning to find ways to quantify that in reasonable ways to apply them to these statistical models. But really, it's this tension between the data that's available at hand and the statistical process with the questions that we're asking about people. So we're asking a lot from statistics. And I think that's really important to remember. Problem number 3, people are weird. People are illogical. We can model optimal locations for people, and it works pretty well. I mean, you saw the result from the Minnesota model, but there are a lot of reasons that people don't behave that we expect them to that aren't logical. We can't know what someone in the woodland period was thinking when they lived in this area that floods like 5 times a year. We don't know. We might be able to figure that out archaeologically, but as far as modeling, it's a challenge right now. I do not have a solution for this, so we'll move on. Problem number 4 is we're using modern data to address questions from the past. So that's a big problem because when we look at anything involving climate change, we can just look at how much the environment of the United States has changed from 12 to 15,000 years ago. It's a completely different landscape. The landscape from 100 years ago was completely different. So we're, again, asking a lot from these data sets. So we're using modern DEMs, digital elevation models, or the National Elevation Data Set. And we need to be cognizant of the scale of the data that we're using and precision versus accuracy. So the big takeaway here is that we need to be cognizant of the fact that we're using really state-of-the-art data that are flown with lasers out of helicopters to look at what happened 10,000 years ago. So something that we can do too is integrate paleoecological data sets into some of our models. Now, I think that we've identified ways to do that, but the application of that is still challenging with the scale of question that we're asking. We're asking questions about on the site level or very local, and we can really address more regional or national effects using paleoethnobotany, ice core analyses. There's been great research done with Bayesian modeling as applied to accelerated mass spectrometry and radiocarbon dates, but it's going to be necessarily multidisciplinary. And that's really a fundamental key for archaeological predictive modeling, is that we're looking at the big picture and we need to integrate multiple kinds of data, which is why you're not just an archaeologist when you're doing this, you're a data analyst. And it's important to remember that you're looking at the big picture and really the intersection of statistics, math, biology, ecology, anthropology. And then one of the big sort of themes that I've been talking about so far is the tension between archaeological data sets and statistical truths. So what you see on the left is an image that I made of an optimized hotspot analysis made from a Moran's assessment of the distribution of sites on the coast of Georgia. So you see that big red spot there, two red spots actually. One's a military base and one is Savannah, Georgia. So of course, there's going to be a lot more archaeological assessments and CRM surveys of military bases. We have Section 110 and of Savannah because they build all the time. It's, well, a ton of reasons. And then if you look at sort of the southwest part of the coast, there are hardly any surveys. And most of archaeology is driven by CRM. It's driven by the growth industry. It's driven by roads, highways, different building. So our sample is flawed. It's always going to be flawed, and we will never really know the true depth or extent of the archaeological resources that are there. Furthermore, we use a lot of different techniques. There are surveys based on 100-meter interval, 20-meter interval, shovel tests that are 30 centimeters, and block excavations. So when we're looking at the scale of our interpretation, the scale of our analysis, it's based on data that were collected unevenly. So we don't truly know if a location is actually absent of points. We know that it hasn't been tested, but that's different than not having a site. So the regression analyses that I've been talking about require binary inputs, those site or no site, for the training variables, like a site point. So a lot of times people, or more recently, people have been critiquing some of these predictive models for using the presence and absence of points. That's required by the regression analysis. So it's important when you're looking also at critiques of some of these models is to look at the reasons that the model was built the way that it was. Another sort of logistical issue that we run into is that when you're running all of these different predictive models, it's based in points, not polygons. The statistical techniques can only be used with points. So that's a big issue because we can weigh the density of archaeological sites, sort of like what the hotspot analysis on the left is. But a lot of times the sites can count the same when we're looking at these big picture surveys. So Etowah counts as a site, a debitage scatter with 3 points counts as a site, depending on state laws. So this is problematic. And what it's really going to take is somebody going through and creating a new scale for this data, significance factor, so to speak. But like I said, with Georgia, we have 60,000 plus archaeological sites. So it's going to take a lot of time to create a sample that more accurately represents the reality of the situation. And that's something that we'll do. It's something that I think will be done, but it is a challenge for the moment because we do have that uneven statistical sample. So a few of the considerations that you need to be thinking about for archaeological predictive modeling is that they can't be treated as static. You need to test, train, and reevaluate at set intervals. And look at the Illinois model for a really kind of well-documented and folks that have done this really, really well. We're using more AI and machine learning tactics to reassess the models, and we can create these sort of fake models and bolster our data sets, standardize our data sets, and say, what if we surveyed everything as well as we did military bases or water reservoirs? Now, that's not going to be useful for the initial reasons for creating these predictive models. It's not going to be very useful for DOT, I would argue, because it's more experimental than real. So also, a lot of these models, the models themselves are built for a predefined set of questions, and the interpretation of the model is theoretical. It needs to be theoretical, but the construction of the model is not always. The questions you ask for the model itself is statistics. So always remember that it's really the math behind the map that you need to be the most concerned with. And then remember too, the scale of the data set, analysis, and interpretation when you're looking at this. So the national elevation data set that's been the background for some of these slides is going to be challenging. Actually, the quality of this is really, really good. So it'll be fine for a local analysis, but some of the more coarse grain analyses that I'll show in a second would not be great for these local interpretations. Okay, so now let's shift to modeling for climate change, which is always going to be multidisciplinary. There's going to be a lot of layers and different considerations, and you always need to be careful with data preparation. So looking at the scale of the data, the purpose of the data at hand, and compatibility. So you need to choose your questions very carefully when you're moving into this next phase of predictive modeling. So here's a really good example of this compilation of data. You have environmental data from Mauna Loa, you have observed data from all over the world, and then you have these inferential statistics to create a model of deviations from the normal temperature across the world. So we have a ton of really, really incredible models at a global scale. So we have the RCP estimates for kind of what we can expect for the Earth in coming years based on different emissions. We have different temperatures, and these are really based on the compilations of many different kinds of sophisticated data. These maps are the results of hundreds of people, thousands of people working on the same or similar questions. However, it's challenging and occasionally statistically erroneous to apply this at a local level. So for example, if you're looking at the RCP scenarios, it would be really hard to apply that to one marsh on the coast of Georgia. We can use this as an estimate of what to expect, but putting a particular number on that wouldn't do us all that much good. It would help to have an estimate, but the precision, level of precision is a big consideration when you're looking at a global scale. Nationally, we're being able to recognize more patterns that would help us. This is a GIF of different animal migrations. And again, this is actually built in R, which you can do all kinds of statistics with, but you need to learn how to program in a language R, tons of tutorials. But you can create images like this. So this is, again, based in math, actually lots and lots of layers of math from lots and lots of different kinds of data, using data from today forward-looking, based on different trends that were identified using other kinds of models. Because remember, there are lots and lots of different kinds of models. This is one. And then we can look at other sort of national styles of data that really help us. Again, this is a GIS built in R. And once you get down to it, you can start identifying what program a lot of these were built in. And then you can actually go back through GitHub or something like that and pull somebody's source code. So if you want to experiment or build on what somebody has done, but at a more useful scale for some of our questions, you can use similar methods that have been previously defined by others, but for other questions. And then at a local scale, this is really useful for our questions, but don't fall into the trap of false accuracy. So these models are limited, and it's our responsibility to know some of these limits. Both of these examples are from SLAM, or the Sea Levels Affecting Marshes model, which is open source software that incorporates some of the global predictions for climate change, and you can apply it to a local level based on national wetland inventory data. So it's all based on open source data. It's all free to use, and it's a pretty straightforward program once you clean your data, of course. So overall, scale is important when you're downloading data, when you're integrating data into your model, and when you're coming up with your different research questions. All right, so now the fun part. How can you try this? As you can see, there's a bunch of hyperlinks in here, and I'd like to go through pretty quickly. So first step, download a form of GIS. If you're associated with a university, Esri is pretty easy. There's tons of tutorials, but they change it pretty often, and it's not very good if you don't have a solid internet connection. QGIS is free and easy. You used to have to program in Python to get a lot done, but now it's a lot more point and click. So if you're just starting out, QGIS is going to be the most straightforward, easy way to get from I don't know anything about GIS to kind of rocking and rolling. R is free. It's really hard, but there's a lot of flexibility. So once you get through the tough part, it's totally worth it. And then another one that I just read about is databasin.org. There are more and more GIS sort of production facilities where you can make a basic map through an online platform. So Databasin is all open source. So if you need a basic map, that's going to be a good way to start. There's tons of online tutorials, and I've highlighted a few of the really good ones that I've seen for archaeological predictive modeling. So Andrew Yeti and Gonzalez Tennant does QGIS for art. He has, I think it's 13 or 14 different tutorials that start with the basics and go up through predictive modeling. So that's really, really good for QGIS. There's different weighted overlays in GIS. There's the SEER Lab generalized linear model, that's made by an archaeologist. That's really helpful. And then Esri has a lot. So be prepared when you're looking for a lot of this. You have to interpret a lot of these tutorials for archaeology. You'll find really good tutorials in predictive modeling for biology and ecology, but it takes some interpretation and application for archaeological questions. And then where to get data is kind of tough. I have a huge list here, and don't give up. A lot of times you have to cycle through a lot of different pages to find the actual database and the actual repository. So you can go to NOAA Earth Explorer. That's usually my first step go-to. There's NED, the National Elevation Data Set, NRCS, which is where you can get different elevation data, but is most useful for soils and the Geospatial Data Gateway. State repositories, depends on your state. Tennessee is really, really good. They just got a great digital elevation model that's like 1 or 3 meter accuracy for the whole state. So it's really incredible. So some states are doing a great job on that. Others, it's all based on funding. There's the National Geological Map Database, which is where you can get geological maps and you can get help interpreting them too. And then otherwise just read a lot, because the multidisciplinary context is really important, and you'll be able to see what other disciplines are doing. There are whole subdisciplines in ecology for data analytics, for predictive modeling. So it's really, really well developed. And you can sort of see what's on the cutting edge for GIS, see what's on the cutting edge for statistics, and then see how we can apply that to archaeological research questions. So here's the basic steps you can learn in a week. Download GIS or through Esri, QGIS, R. Learn how to download data, add the data to your GIS, set or convert the coordinate system. That's kind of the first step. And if you're having problems with your data, this is probably where the issue is through your coordinate system. Clip to shape, that's going to depend whether you're using vector data or raster data. And then my favorite thing is the 3-strike rule. If you mess up 3 times, stop, walk away, and when you come back, you'll probably get it. I've been doing GIS for about 12 years, and it's worked really well. I'll be working, 10, 11 at night, cannot figure something out, start up in the morning, and I get it first thing. So 3-strike rule. So I love talking about this stuff, clearly. Please contact me if you have any questions. That's not my phone number, but that is my email. So lindsey.cochran@uga.edu. And I would love to talk to any of you about more of this. I have plenty of tutorials saved, lots of different articles saved, so I'd be happy to share any of that with you. So are there any questions, anything that people would like to talk about? I know that's sort of an overload of a lot of the information that's been going on, but it should be a pretty comprehensive starting point for those of you that are interested in archaeological predictive modeling.